Well, neural networks have made their way everywhere. Hidden behind the AI buzzword, they are speeding up very concrete calculations in many sensitive areas of engineering. So what are they and what do they do? Simply put, a neural network is just a type of generic function that you can use to fit complicated data. This might not sound all that exciting, but the benefits can be huge when used cleverly. To see why they are so useful, let's assume that you've collected some data looking like this. This could be the amount that someone spends in a shop versus their browsing time, or the efficiency of charging a car battery versus the ambient temperature, and so on. Since I've studied fluid mechanics, I'll say that this data represents how often I've measured the wind blowing at different speeds on top of a particular hill. Now, if I want to do something useful like building a wind turbine, I'd like to know stuff like how often is the wind going at 10 meters per second. I don't have a direct measurement for this, but you have probably guessed that the answer is 15 days per year. Since you won't always be there to help me, I'll build a model of the data so that a computer can answer these questions for me. I have two ways to go about it. The first way would be to hire a master or PhD student to derive a model from first principles. For example, the wind speed can't be negative and air is never exactly still, so 0 meters per second is not likely to happen. Positive speeds do happen and should vary continuously. There's no upper limit on the highest velocity, but you could argue that large speeds should occur exponentially less often. In the end, there might be some coefficients left that we can fit experimentally using our dataset. All this work is very valuable. It's grounded in physics, and if you're the first one to do it, you should absolutely publish it. But I could also want the computer to do what you did in your mind and just give a number that looks legit, given what we know. There are a lot of generic models that I could use for that, and things like exponential and power functions fit a lot of physical phenomena, but in this case, I can't find anything satisfying. Let's admit something right away. Linear regression is awesome. It works really well on really large parts of my data, but the points just don't align forever, so I have to use something else. This is where the neural networks come in with the simplest trick you could possibly think of. Instead of trying to fit an infinite line, they try to fit a half-infinite line. Something that is a linear function of positive inputs, but disappears to zero for negative inputs. A function that in the business we call ReLU. So how do you use that? We can scale and shift the ReLU function thanks to two empirical coefficients, the weight and the bias, which we adjust to get the best possible fit to the data. Okay, that's slightly better, and we can shine at cocktail parties by saying that we've used a numerical equivalent of a neuron. But let's try to do better. We can use a second ReLU function and scale it and shift it independently so that when we subtract it from the first one, we get something yet slightly better. Add a third ReLU function and we're in business. Graphically, we've connected a bunch of neurons together, so we're effectively using a neural network. What's very interesting is that even if my data gets more complicated, I'll be able to get a good match simply by adding more neurons. The operation that combines all the neurons together can be seen as a neuron itself, which is placed on a second layer and gives depth to the network. In practice, we can balance the width and the depth of a network to fit complex functions using an overall reasonable amount of neurons. Since the ReLU function is so simple, making calculations with neural networks is fast, and it works even if you have not one, but hundreds or thousands of variables as input or output, like for instance the pixels of an image where you try to segment areas of interest. This makes neural networks a ridiculously powerful generic model which powers the vast majority of deep learning applications. The only notable alternative at the moment is the transformer, a type of network that uses attention as its mechanism instead of running neurons, and which we have covered in another video.